So in the drawing of concrete, we had talked about this variant of the problem where we were talking about a steady state. And we found that when we applied the assumption of steady state, and we did that directly to the interior material balance, right? So looking at the material balance, we just set steady state. So we set that to a 0. And when we did the first integration, so we integrated for y here, then of course we had k equals this. And then again, we could separate the variables. So we separated a y out, and then we were integrating this. And then we did the second integration. So integral of this is minus ln of 1 minus xa. And then the integral of this is k1y, k2. And then we applied our boundary conditions. And of course, our first condition is that at the base, there's no flux. And so if you apply that, you get the extremely restrictive condition that if at the base there's no flux, then it means that this gradient is equal to 0 there. And that means this K1 must be a 0 as well. So this then completely removes our dependence on Y. But this is consistent with that the flux must be 0 at the base and that it's completely steady state. So under these conditions, we found that the only possible steady state was a complete equilibrium with the air mole fraction of water. So that was quite restrictive. So although it is a solution, right? Remember that this chapter, we are looking at how to solve the equations. So this is a solution. It's a very specific solution. It only applies at steady state. And you could say it doesn't help us that much because in a sense, we already expect this result. So that's what we saw and talked about yesterday. Just checking there, are there any questions or comments on this work? By the way, I have uploaded this set of notes, but it hasn't synced as yet. So when you visit the site, it might not be rendering this result for you. It should show up later. So please do just follow along on the screen for today. Excuse me. Okay, so this was the first attempt at solving our drawing of concrete problem. Now, in this tutorial session, we want to look at 2 more possibilities. The second variant, which is what we'll talk about here, is where we consider the air film more carefully. So we had introduced the notion of a film, of a film theory, and now we want to use that to see if we can develop an alternate boundary condition, which is not so restrictive. And let's just check in the chat. So I can upload it. What I would do is print this to PDF and I can copy it to the Learn site as well. Okay, that's fine. In fact, let me do that quickly so that we all have access to what we're seeing on the screen now. So remember, if you want to do it, you click read mode, then that will render everything in one view. And then you print this, just that on this Apple device, it takes me a bit more work. It's a little harder to do basic things. Okay, save to PDFs. And okay, 1 second. I'm just going to upload this to our Learn website so that we all have this PDF. Almost there. Okay, it's done. So if you go to course metadata, let me just show you through share screen here. Where's my Zoom? Okay, so if you go here under course meta, you'll see this 2EF PDF print. So please open that up and you'll be able to see the same thing that I'll be showing on the screen now. Okay. Any questions or comments now? Okay, thanks. All right, let's get into it. Okay, so that's what we were talking about. I'm just going to turn off this read mode for myself. So here, so that was what we worked through, and we found that we got that solution, which is kind of a trivial solution. We had also yesterday introduced the notion of not yesterday, on Monday, we also introduced the notion of the film theory. So we said that in some space that fine, you may have a variation in your concentration. So it might well be the case that near an interface, the concentration is varying, but that influence will only last for so long. There will come a point where your concentrations become the bulk value. And so we said, if everything is can be regarded as, if all the changes are regarded as happening in a certain small space, then we can define that space to be the film, and our balance written in terms of that film can then account for whatever variations we have, and we don't need to integrate over the whole space. And that's in effect the second variant of what we'll try in solving our drying of concrete problem. So we are going to rethink the way we look at this drying of concrete. And of course, our emphasis has been very much on the concrete itself, right? The evaporation of water from that concrete. And in fact, the majority of what happens is not the driving force for this. Of course, there's diffusion driving force that pushes the water up. But the main instigator, if you like, of this drying is what's happening on the surface, right? The surface evaporation of that water. So let's draw that. Let's imagine a little film that's sitting at the surface here. So this is, of course, an imaginary film. So we have air that's flowing through this, that's flowing around up here above the slab. So air is flowing, and we have some gradient in terms of our mole fraction of water. So there's some bulk mole fraction of water, and then near the slab, we have a higher mole fraction of water because water is leaving that slab as well. So we expect to see something like this near the slab. So just drawing this as let's just draw our concentration profile like this. So we've got some air concentration of water, and then we also have some profile like this in the air that's near to in the air that's near to the surface. So we see here that we've got there's a low concentration of water in the air, but when we are near the slab, because the slab has water diffusing out of it, then we'll have a certain other concentration of water on the surface. And then as that water is diffusing into the bulk here, that concentration goes down and it reaches the bulk value, the air value. So that's how our water profile looks eventually, right? We know we have some variation in the concrete. We also have an equilibrium shift here. We know that these are two different phases, the concrete phase and the air phase. So there's an equilibrium shift. And then just above the surface, we have some concentration there, and then it varies, like we said. So we could say, well, in the air, all the action is concentrated in this small zone. So why don't we apply film theory there? And let's just say that there's a simpler way to represent everything going on there. So to do that, we will go ahead and write we'll write the film expression. So let's just open up a new PDF here. Let's see. That's that one. Okay. Yep. So let's just do this in a new document then. Okay, so we would like to write this expression for the film here. We would like to understand the molar flux in the air that's sitting above the slab. And so we said last time that flux, the flux of our water in the air, that according to film theory could be represented more simply as Kc times the concentration difference. And if we look at the concentration difference, we can see two concentrations here. We can see a bulk concentration of water in the air, and we can see a surface concentration of water, which is just above the slab. So we can write this as Ca bulk, and this is the concentration of water just above the slab. So this is going to be where Y equals H plus, right? So those are the two concentrations. So in this problem, right, so that's just to outline a starting point. In this problem, we are given the diffusivity of air, and we are told that we estimate a film thickness of, this is about 2.5 millimeters, right? So it says here under the current flow conditions. So that's because there are various correlations available in the literature that help us estimate the thickness of a film. So we have the film thickness simply given to us, and we have the diffusivity. We are also told the mole fraction of water in the air is 0.0216. So if you go and look up the standard mole fraction of water in air, it is about 0.02. So this one is slightly higher. So this is probably closer to sea level. You've got a slightly higher mole fraction of water in air in this problem. So that's what's in the bulk, right? And then it also says here, the initial mole fraction of the water in the concrete is this value, right? 0.105. It gives us the length. I think I do actually have numbers for these, so I'll just re-render this page with the numbers. And then we want to know what's the initial evaporation flux. So how fast is water evaporating? What's the flux, evaporation flux from the surface there of water? And then what's the evaporation rate? And given that we are now using film theory, now we know how to incorporate film theory here, what does the boundary condition become? Right, so this is the first problem in our tutorial. So you can get started on this. And I'm not quite sure how to run a tutorial on Zoom, but if anybody has a question, then of course, raise your hand and I'll give you time to work through this. So let's take 10 minutes, ask whatever questions you like, and I'm going to hold off. It's not so easy, but I'm going to hold off giving you any kind of solution until after those 10 minutes. So it's an important 10 minutes. Don't just wait for me to start working through the solution there. In that time, really think about how would you use the form theory, how, given this information, what would you do with it? Because once you start looking at a solution, everything looks pretty straightforward. You'll never know where you're going to get stuck until you try and think your way through it yourself first. Okay, so let's try and run a tutorial like we normally do, and please work through this first question at least. I'm just going to add these dimensions for L and so on, so long. Okay, any questions or comments so far? Any ideas about how to start handling this one? So first off, we had said that we have, in form theory, we will simplify everything that's happening on here. So we would just take the straight line difference across the space. So let's use a different color for that. So according to form theory, you would just draw a straight line through those 2 points. Okay, so that's just to give you a starting point. You can continue with that. Okay, yeah, I'll work on those lecture uploads today. Yeah, as I mentioned, I've got a new setup and it's taking quite a while to get everything back to speed. So I'll upload the videos later today. Okay, so let's start looking into how to use what we know about film theory. So we've said we know that actually the concentration profile here is more of a curve, but in film theory, we approximate it with a straight line. And we just go ahead and say the molar flux according to that just looks like this, right? So the molar flux is simply proportional to that concentration difference. So CAB, we can see here, that's the concentration in the bulk. So that's that concentration. And then at this point, we are just in the air. So we are at a point just above H plus. Remember, the height of the slab is H. So we are looking just above the slab into the air. So to specify that, we said Y equals H plus, right? And so that's the concentration of water in the air just above the slab. And we can see the concentration there is higher than in the bulk air. And that's because, of course, we are releasing water from the slab there. So anyway, that's our molar flux of water into the air. And we can say that that flux there in the air, that flux must be the same as the flux in the slab just beneath the surface, right? We know in the slab, the flux of water is changing at different points. If we choose different points, if we choose different points along this height, we will get a different flux at each point. But just next to the interface, the flux of water there must equal the flux just above that point. And the reason it must be equal is that there's no space here for any water to accumulate, right? And understand this carefully. Sometimes we say two rates are equal if there's no change in time. Sometimes because of steady state, we say two rates are equal. Here, we are not talking about a steady state. We are talking about the fact that we are looking just across an interface. So if it's a perfect interface, in other words, if we are looking at points in space just to the left and just to the right, or just above and just below, right? So in other words, there's no kind of there's no kind of finite material in between the two. It's a pure interface. Just there's water in the air, and then there's water in concrete. There's nothing in between those two. So at the interface itself, right? Imagine the skin of that interface, right? That skin has zero volume. It's not even the right word to use, because skin does have a volume, right? If your skin, if you think of taking off your skin, it's going to have a certain thickness. Okay. We don't have to be so gory, but that skin doesn't have the skin here. The interface here has no thickness. So if there's no thickness, there's no space to accumulate anything. And so the flux just above the surface must equal the flux just below the surface. And we've chosen to express the flux just above the surface using film theory, using this expression. So we could be a bit specific here and say this is, of course, at y equals h plus. And then we can say the flux of water, so NA, and this one is in the concrete. So concrete, so the flux of water in the concrete, and this is of course going to be at y equals h minus. That must equal the flux in the air. But what's this also equal to, right? Your flux of water in the concrete, what expression can we write for that? Well, we can always write, if we look at our material balance for the drying of concrete, our flux is this. So this is the flux. well, we said stagnant. So if it's diffusion through a stagnant component, that is our flux. We said for the drying of concrete, that is the appropriate flux to use. So we can write here that this expression, oops, where am I? Yeah, we can write here that our flux, which is minus C DAB, C DAB, and that's divided by 1 plus XA, and that's times dxa, dz. Then that's actually the flux that's inside the concrete. And because that's equal to what's in the air, then this is equal, these two things are equal. So we can write here that this applies at the surface of the concrete. So on this side is the evaporation rate. This is effectively the evaporation rate. Strictly speaking, or more generally speaking, this is just the flux of water through the air above the surface. And this is the flux of water into or through the concrete near the surface. So we should specify this as near the surface for it to be equal to the left-hand side. So this is dCA dz at the surface, which we write as y equals h plus. And we should write that strictly in here as well. Y equals h plus. Right, so this is now a boundary condition that we can use. We can see that we have a derivative here on this side, and well, let's just park this result for now. So this is a new boundary condition that we've discovered by using film theory. Because we can estimate a flux now, we are able to specify a flux inside the concrete at a specific point. Okay, so that's one boundary condition we can use. Now go ahead and write down quickly the other boundary condition that also applies on this surface. Okay, and we won't spend as much time on the second one because we have talked about it before. So boundary condition 1, this is new for us. This is now saying the evaporation rate can be used as our molar flux. The other boundary condition is simply that we do know the concentration at the surface. So we can say that the concentration of water at the surface just inside the concrete, y equals h minus, that is equal to the equilibrium value. So we've got an equilibrium constant, and we must multiply that by the concentration of water in the air. So the concentration of water in the air, that's going to be at y equals h plus. So that's our second boundary condition. Okay, now what we'll do here, well, let's return to the question. The question is actually asking for something a bit simpler, right? In this question, we want to know, let's see, that's the diffuse, am I looking in the right place? Yeah, that's the previous chapter. So in this question, We are asked for the initial evaporation flux and the initial evaporation rate. So you can calculate the evaporation flux, first of all. Use the information given in this question, see what's relevant to calculate the evaporation flux. We've just said we can use the film expression for the evaporation flux, but you need to choose the values. So there are lots of mole fractions here. So go ahead and calculate your initial evaporation flux. Right, let's just take 5 minutes to do that. So this part is really straightforward. If you look at your flux expression, is that? So if you look at this film expression, you've got a Kc here. Well, number one, we don't have Kc. If we look at what the problem has given us, it has given us a diffusivity. So we have a DAB. We have diffusivity, and we also have the film thickness. So we do have the delta. So we'll use a lowercase delta there. But we had showed in the previous, when we introduced film theory, we proved that Kc equals DAB over sigma. Right, so that's all we need to do. Take our diffusivity divided by the film thickness. It was about 2.5 millimeters, and DAB was given. So that gives us Kc. So we have a value for Kc, and then we want to subtract. We want to multiply that by the difference between these two. So CAB, if we look at our drawing here, that's the bulk concentration of water. So that is clearly the air concentration, which is about 0.02. So we can say here this, let's just do it like this. So CAB is 0.02. And yeah, I should be saying this as NA. NA equals Kc. This is CAB minus CA about Y equals H plus. So our CAB, our bulk concentration of air, is this value. And then our concentration of air just above the surface there, we don't know as yet. So we don't know this value. But can you give me a value that's close to that? Right, and a kind of clue here is it's asking for the initial evaporation flux. Right, any ideas here? We want the initial evaporation flux. So what should be the concentration? Right, we want to know the concentration in the air that's right next to the interface. What should this concentration be? No takers? So what should the concentration of water in the concrete be initially? We are simply told that the concentration or the mole fraction of water in the air initially is 0.0, or not 0.0, it's 0.1, right? It's 10% of the concrete is water. Now that's in the concrete, and we have to be careful here. This is referring to the air. So we need to multiply by the equilibrium constant for that. And we were given the equilibrium constant. It might have been only in the, I think it was given in the original statement. And of course, now we are looking at all the variants, but that equilibrium constant still applies. So we look at the concentration or the mole fraction in the concrete and multiplying by the equilibrium constant, that gives us the concentration in the air. Well, a couple of corrections I should mention here. First, these are mole fractions. So whereas this is in concentration. So I'm assuming here that we are also writing a total concentration out here. Then we can multiply by mole fraction. So that's the mole fraction in the air, bulk air. This is the mole fraction in the concrete. And by multiplying by the equilibrium constant, we get the mole fraction in the air that's just above the surface. So now we can see we are subtracting the right quantities from each other. And everything is specified. So your diffusivity is given, the film thickness is given. The concentration of air, you can just look that up, right? You can take the density of air. It's between 1 and 2. It's probably about 1.2 kilograms per cubic meter. You can take the molar mass of air, right? It's 80% nitrogen, about 20% oxygen, and as we are saying, a little bit of water. But anyway, you can get the molar mass and the density of air. And so you can, of course, convert that to a concentration. So we've got the total concentration of air. And the equilibrium constant we were given in the original problem statement. So we have everything we need to estimate this molar flux. So that gives us effectively the evaporation flux. And then the next part of the question does ask for the evaporation rate. And that's a simple matter of saying, so if this is our evap, then it's simply going to be the flux times the area that we are fluxing through. And of course, this is, it has 6 faces. This is rectangular geometry. So the area that we will be diffusing through will be LW. So in the problem, the length and the width are given. So it's 2.37 meters long, 0.7 meters wide. So that product is the area that we are diffusing through. We also have that it's 0.2 meters, 0.18 meters high, but we are not talking about diffusing in those directions. That's the sides of the slab. This is the area of the top and bottom faces of the slab. So that's the area we want to multiply by. So that will be the rate of evaporation. Okay, any questions or comments there? Okay, now let's look at, the next question asks, develop the boundary conditions incorporating the evaporation rate at the surface. Well, we've already done that. We said here, if this is our evaporation rate, then this applies in the air above the slab, and then we said that flux must equal the flux in the concrete, and the flux in the concrete is this. So our boundary condition now looks like this. Okay. So there's a question in the chat: how do we get 0.02? So that's that is the saturation mole fraction of water in air. And if we look at the question, it says here, in this instance, remember, every time I regenerate the question, it changes the numbers a bit. So what I typically do is I look up standard values for each quantity, and then I add a small variance. So if you look in my code, when you saw me learn spacing things here, I'm basically taking some range around an average, and we are choosing a random value in that range. So yeah, that's why it's 0.01. So if we are looking at this instance of the question, then that's the value we should be using. Was that what you were asking there, Vanya? Sorry about the noise here. I'm actually in the office on campus, and yeah, the parking lot outside is a bit noisy. Then is sigma the film thickness? So this is delta, right? This is a lowercase delta. Sigma is this symbol, sigma. So that's a sigma. So this delta does look like this, but it's this is a delta. Yeah, so delta is the film thickness. So if you look at what we said on Monday, yeah, the difference in positions. So the delta is the position where the concentration is 99% of the bulk concentration. So yes, that is the film thickness. And then the question is, why do we multiply Ca and Ke? So here, why did we have to multiply by this Ke? So this is, of course, the concentration of water in the concrete, right? Initially, we had 10% of water in the concrete, or the way I should say it is, the mole fraction of water in the concrete was 0.1. But this is looking at the concrete, whereas this molar flux is in the air. So if this is the flux in the air, this concentration difference is air concentration differences. So it's referring to the concentration in the bulk and the concentration in the air above the surface. So that's an air concentration. So to get the air concentration, what we are saying is the air is going to equilibrate, right? The air just above the surface will equilibrate with the concrete. So the concrete has one concentration here, but the relevant concentration for the film is the air concentration. So we need to multiply by the equilibrium constant and correct it so that we get the air value. And I know I've drawn it as if it's a small distance here, but actually, if you think about it, this is air, right? So this is a gas up here, and this concrete started out as a liquid. So it's a complex liquid mixture. So the density difference, it's on the order of 1,000. So there's a very large difference between these two values. But the equilibrium constant helps you translate between the two. Does that answer your question there, Sahil? Okay, so that's our expression for the form, and we equated it to our diffusion flux, and so that's a new boundary condition that we have now. Okay, and let's see, is that another? Okay, so that's yeah, those are the two there, and then yeah, so we've completed that question then. All right, moving on. Let's look now at the so-called quasi-steady state approximation. So we've heard of unsteady state, we've heard of steady state, but there is another state, the quasi-steady state. So we say something is in a quasi-steady state when things are still changing. So in quasi-steady state, things can still be changing, but they can also be settling down fast enough that we can regard it as being in a kind of steady state. Let's take an example here. So let's say we have some space, So let's say there's a block of some medium. Let's say this is a pool of water or something like that. And let's say we have a concentration down here, which is maintained at a certain value. So let's just use this color. So we are maintaining a concentration at the base of this block at this value. And up here, we are maintaining the concentration at some other value. And so let's say this steady state developed, right? Because so maybe on this wall, there's a certain concentration. And so we are stuck to a certain concentration down here. And let's say up here, we can throw in some solution and set the concentration out here. And then through diffusion, we accomplish this profile. So this becomes our concentration profile across the space. Now, what could happen is sometime later, we decide to go ahead and use a different, let's say we go and add, let's say we add some other value. So we throw in something else. So we add some other value to the space. And so we change the concentration at the surface here. Now, what we expect to actually happen is that since the whole space is following this line to begin with, that there's going to be a slow shift. So up here, fine, we are free to pick the concentration because we can just throw something onto the surface and change the concentration there very quickly. But then what we expect to happen is that that component will then have to diffuse in and then penetrate the whole system until it eventually settles down to a new profile. So we expect to have something like this happening. We expect that at some intermediate points or some intermediate periods, we expect that we'll be going through a transition where we are switching from the earlier steady state, right? We expect that when we just forced the concentration to this new value, that A would have to diffuse in, and then slowly the whole profile will shift over and settle down to the new profile. So that's what we expect to happen. That's why we've been writing the balances that we have, because it takes time for things to settle into a new steady state. And so we need unsteady state. So that's generally what would happen. If it's the case that this component can diffuse very rapidly through this medium, then it may be true that component A very quickly achieves its new steady profile. So instead of instead of our concentration profile taking a long time to transition and settle out to the new steady state, then we could say, well, then we don't need the whole unsteady state balance. We can just solve for the new steady state. We can just solve for steady state, and that will be our concentration profile. Or another way to look at it is the moment I move the surface concentration, the whole profile shifts almost immediately. So if that's the case, so if that's the case, this whole profile is moving as I'm shifting what's happening on the surface. So that's what we call quasi-steady state. It's not perfect steady state because we are talking about a value moving in time and the whole profile is moving in time. But it's a kind of steady state because as we shift this value, the whole profile equilibrates, if you like, right? It's not quite the right term to use, equilibrate, but let's just use it. It's as if our fluid equilibrates, it settles into this new value so quickly that it's as if we are always at a kind of steady state. So it's not at steady state because this value is moving, but the whole system is so quickly settling into the steady state that it's as if it's at a steady state. So that's why we call it a quasi-steady state. So we are going to use this quasi-steady state in this concrete example. We are going to say now that the evaporation change here is rather slow, right? We know that we are losing water at quite a slow rate, right? It is evaporating, but this is not like a reactor where we want things to happen within 20 minutes. We don't want long residence times. We want high productivities. We want things to happen on the order of minutes. Whereas the drying of concrete is actually quite a slow process, right? As we said, actual drying happens over 99 years. But even for concrete just to set and take form, it can happen overnight. But still, that's the order of magnitude, right? The time is on the order of days. The time for things to happen is on the order of days. So if evaporation is happening on the order of days, and if we are really talking about molecules diffusing through a few centimeters of slab here, we can well imagine that we are going to go through some quasi-steady types of profiles through this slab here. So we can apply a quasi-steady state approximation to the profile that we'll be getting through the slab. And that's going to open the way for us, in a sense, for getting to our solutions. So we've got two new concepts now, right? Number one, we've got the film theory. And through film theory, we are able to get a different boundary condition. And now we also have quasi-steady state. We are saying, yes, we know things are evaporating, and so the surface concentration is dropping. So that's true. But still, we are hoping to claim that this whole profile shifts fast enough compared with the evaporation rate that we can claim a quasi-steady state there. So that's the concept of quasi-steady state. And we are going to use that now in creating the next variant towards solving for the drying of concrete. So again, we've got the diffusivity of air, we've got a film thickness, we've got a mole fraction of water in air, we've got an initial mole fraction of water in concrete, the dimensions of the slab, and now it says using quasi-steady state, develop the expression for the profile at any instant in time. Okay, so take 5 minutes and develop the quasi-steady state version of the balance. In a normal tutorial, I would walk around and peer into your books. So I'm just going to kind of pace my office to simulate that. Okay, so in fact, we have done this already because we did do steady state last time. It's just that in that case, we had used a different boundary condition. But we had said, number one, we always start with this general material balance here. And then we applied steady state. So when you apply quasi-steady state, it's not like it's different. Quasi-steady state means that dx dt is going to be 0. It also does mean that some of these values may be time dependent still. So that's what's different, that it's just what you get left with can still vary with time. But if you solve this equation, you'll get, even in the face of time changes, by solving this, you'll get the solution at that instant. Okay, so that's your same steady state expression. So the first integration gives you a constant, and the second integration, if you separate the variables, gives us this. So this is the same as what we saw on the Monday, right? But now we want to use these form boundary conditions instead. So we said we've got Kc times delta Ca, and here, I should actually be using divided by the 1 minus Xa. But anyway, this is the molar flux. This is supposed to be the interior molar flux. And so we can say that's a boundary condition. And well, I see I do use that here. So, so that's our new boundary condition. I should point out here, there is a new variable that we don't quite know how to get, which is the concentration of A in the air just above the surface. So that's not given to us with the question. So that's something new, if you like. We know this does relate to the concentration just inside the concrete, but that's also unknown, right? So those two unknowns, we can say through this relation, through the equilibrium relationship, right, that's the equilibrium relationship. The concentration in the concrete is equal to the concentration in the air times Ke. Just be careful, I may have used Ke. We need to do it consistently, so we need to decide whether this Ke needs to be multiplied by the air or by the concrete. So the way, let's just fix for now that Ke belongs to the air. So you have to multiply it by air and get the concrete concentration. So we must just correct it if we are using it the other way around. Okay, so just watch out for that. But anyway, that's what we have there. And then we can also try and split off the concentrations here. So if we divide through by the concentration in the concrete, right, the total concentration in the concrete, then Ca becomes Xa. And here, we don't simply extract a concentration, because now this is air concentration, right? This is at H plus in the air. So the total concentration there is not the same as the total concentration there. So they don't cancel. So we have to keep this total concrete concentration here. But this is the other boundary condition. So you see, you have your two boundary conditions now, one being an equilibrium boundary condition, and the other one is it's this differential boundary condition. So we call these mixed conditions, right? That you have a fixed point in the one, and you've got a derivative in the other. So the first boundary condition has a derivative in the space variable, and the second boundary condition has a fixed value. So in the concrete, there's a fixed value for the mole fraction. So those are our two boundary conditions, and we do have this general solution now. So what we can look at doing is applying, let's say we apply this boundary condition first. Well, we can see that dx dy, or let's just look up here, we had integrated, when we integrated our material balance, we got this form. So looking at this form, we can see here that this K1 equals this. And for this dx dy, we have an expression. So from our boundary condition, we have dx dy. So at the surface, dx dy is known in terms of these other quantities. And so we can substitute that in our balance. And then that gives us one relationship to get K1. And then K2, comes by looking at this expression. We now have an expression for x as a function of y. So we can substitute the value of y in this function for x, right? So we stick a value for y, which is going to be h here. So y equals h. That tells us the mole fraction just inside the concentration, just inside the concrete at the surface. And so that gives us the mole fraction in terms of K1 and K2. And then when we apply it in this boundary condition, then that gives us the new relationship that we are looking for. So by combining our boundary conditions with our solution, we are able to find these constants, and then that gets us towards the solution that we're looking for. Any questions or comments there? Okay, so that's the outline for solving this. So go ahead and substitute the values and estimate your K1 and K2. And you'll find that there's an extra piece of information that you might need, right? And but anyway, I'm not going to spoil that. Just go ahead, work through that, and then so I'll leave you to work through those numbers. Let's now look at the third problem. So now we have a problem where there is a material balance with fixed endpoints. So let's just read the question. So we are told that there's an oil spill in a canal. So there's an oil tanker that was passing through a canal, and it spilled 132 kilograms of petroleum. The canal has a depth of 8 meters and a width of 73.68 meters, and it's 247 meters away from the dock. So how long will it take for the maximum concentration to reach 5% of the original value? How long will it take for 10% of the original concentration to reach the dock? So this problem is a typical axial diffusion problem, right? If you think about how to model this, well, actually, take 5 minutes and figure out how you'll write the material balance around this. So I actually have to walk around in my office to stop myself from going straight into the solution. So much like the tutorial. So So in this case, you've got this tube. So let's just do a new drawing here. So we've got a canal, and we have a dock at some point in the canal. There's and then we have an oil tanker somewhere in this canal, and it has spilled its contents. So let's just set it back a bit. So, so we have our petroleum that has spilled at this point. So let's just do the spill there. So we are given the mass of petroleum that's spilled, and we are given the dimensions of the canal, at least in terms of the depth and width. So in terms of this distance and the distance into the screen. So that's basically the cross-sectional area of the canal if we multiply those two together. What else? We want to know how long it's going to take to reach certain values. And, well, we need a diffusivity as well. Oh, it's down here. So the diffusivity is also given to us. And if we think about what we're doing here, we basically have a concentration at a certain point in our system. And we can see, because of the spill, we basically have a high concentration of our component. Our petroleum, we know it's a complex hydrocarbon mixture, but by the end of the day, we can always we can talk about an average molecule or something like that. So we're just going to think of it as one component, petroleum. And we have a high concentration here, and we have a low concentration everywhere else. So in this canal, we assume we didn't have petroleum in there originally. So after the spill, clearly petroleum is going to diffuse in all directions here. We will make a simplifying assumption that it will instantaneously mix in this direction. So you have one concentration that applies here. And then we are going to look at the diffusion in those directions. It does look symmetrical, so we can anticipate that we will have a boundary condition, a kind of symmetry boundary condition that applies. And on this end, we are concerned with how long it takes for the petroleum to reach a certain level here. And we are also interested in how long before the concentration here drops to a certain level. All right, so take a minute and write the balance for this. So just for the sake of practice, develop the unsteady state material balance that describes this situation. There's a question in the chat. In the previous example, how do we get the equilibrium constant value? So yeah, it's not something that you calculate or anything like that. It's simply given to us. So what I said at some point was the original problem where we first posed the drying of concrete case, we had specified a KE value. So if you just look up in chapter 2, the drying of concrete, you'll see an equilibrium constant is given. So it is a value that's given. Yeah, it's not something you derive or anything like that. Okay, so in developing this, the balance for this case, this is nothing but you would develop this in the same way that we develop the expressions for the drying of concrete. So you would pick a dimension here. So it would be natural to call the axial length Z. So we are expecting that the petroleum will spread in the Z direction. And because it's a canal, we expect that in this direction, it's a small, that's small in comparison with this distance. So we would take it to mean that it's well enough mixed in this direction. And also in terms of the height, right? So we can think about the height as well. But we are going to assume it's well mixed in the cross section here, and that it's just in the one dimension that things are changing. So we'll write a balance between Z and Z plus delta Z. And there we would use the same development that we had. So here, for instance, if we look in chapter 2, so the same developments as we had for the drying of concrete, we would have a delta Z this time. And then, yeah, the rate of change of the concentration there. We would have a molar flux in and a molar flux out. And then we were given the height and the width of the canal. So the cross-sectional area here. So we would cross-sectional area there. And so we would end up getting the same relationship here. And we would want to substitute for the molar flux. In this case, it's petroleum against water. It isn't a reaction, right? The petroleum is diffusing against the water. So it's not as if water is going to be stagnant or something like that. So we could anticipate equimolar counter diffusion. The problem doesn't really say, right? The problem doesn't tell you what to use there. So if it doesn't, right, you do have to say something about this. So you do have to make a decision. So you would run through it in the same way that I just described, right? Number one, you would say, well, it's not as if these two things are reacting. They are just occupying the same space. They're not reacting. So the one is going to displace the other. So I think it's more like equimolar counter diffusion. So assuming equimolar counter diffusion, this term will vanish. And it will just leave us with Na equals the second term here. So it would actually be a simpler expression than our drying of concrete. And our eventual material balance, I'll just write it separately here. The material balance would look like this, just separating these things. So we would end up with dCA dt equals dA, and I'll call it a DAE as an effective diffusivity. So when you have large numbers of components and so on, instead of talking about mixing rules and things like that, I just call it an effective diffusivity. And that is, of course, it's going to be a second order derivative in the axial direction. So d2Ca, d2Ca dz squared. So that's going to be our material balance. And then we'll want to specify our boundary conditions. We can see we'll need 3 of them, 1 for time and 2 for the position. So in terms of time, we can say that maybe let's sketch the function. We can say that initially we have no petroleum in the water in this canal. So there's no petroleum except at the position where it spilled. So we could say there's a kind of function like this. We can say there's Ca equals 0. And we would say this applies for x not equal to 0. So let's define 0 to be the position of the spill. So x being negative numbers means to the left, being positive numbers is to the right. So at x equals 0, when x is not equal to 0, the concentration is 0. Of course, this only applies when T equals 0. So initially, we have none of the petroleum anywhere other than at 0. So at 0, we have some non-zero value. Yeah, at 0, we have a non-zero concentration. So where x is equal to 0, it's equal to, and I'm just going to call it a constant here. But actually, there's a special way to represent such a discontinuity. You can read about the Dirac delta function, right? That's a special function. We'll spend a fair amount of time on that in 3rd year in your reactor design class. But for now, I'm just going to say there's a certain amount of petroleum initially at x equals 0. So this is our initial condition, right? T equals 0. It is a function in 2 parts, but it's not additional, it's not conflicting information. It's just to cover all the possible x values. So that's our initial condition. And then we also need our boundaries, and we can say, so the BC1 will say simply that CA an infinite distance away, so x goes to infinity equals 0. So when you look far enough away from the point of the spill, it's equal to 0. And the same is true on the other side. X goes to minus infinity. There's nothing there. And that's for all time. So far enough away from the site of the spill, there's no petroleum. So those are our boundary conditions. And this equation, or the set of equations, right? This is the interior points. These are on the boundary. For these conditions, our well, there is a solution. There does exist an analytical solution for this case, and it looks like this. So, yeah, I spent some time debating with myself, should we go into a full thing on differential equations and how to solve them? So eventually I came up with, well, I'll write the notes on that. So I started writing the notes on how to solve 2nd order ordinary differential equations. So I haven't uploaded this yet, but yeah, these notes are under development. So there's this one. So you can derive particular cases, particular solutions for a second order ODE. And all our equations are second order ODEs, right? If you look here, we have a second derivative and a time. And if you look at the cylindrical case, we did have in the two spatial directions, we had a second derivative. So in all cases, we have a second derivative. In chemical engineering, I don't think we ever go above a second order in terms of any spatial variable. So that's why it's useful to know this stuff, right? Learning, it might seem to you, oh, it's only second order differential. What about third order? What about fourth order? But actually, knowing first order and second order will get you very, very far. So I'll make these notes available. It will come up in your maths class, but for now, just you can read ahead, right? So there does exist a solution to this specific problem. And it looks like this. So that's the solution to this case. You'll see this new variable m. So this is the area density of the mass that was spilled. So the mass that was spilled is this much, so 132 kilograms. And the area over which it was spilled was 8 meters by 74 meters. So 132 divided by 8 times 74, that is your m. That's how you calculate m. If you look at what else is in this equation, there is a diffusivity here. So this DAE, which is given with the question. So DAE is known. The only other variables then are x and t. So if you pick a point, right? So for instance, here, okay, we'll come back to this one, but here it's asking how long will it take to reach the dock? And the dock is that distance away. Well, let me not go ahead and answer these questions using this solution and the specifics of the problem. Okay, so for the first part, we want to know how long it will take for the maximum concentration to reach 0.5 of the original value. So if we think about that, we first have to figure out where is this going to be, right? When we talk about a maximum concentration, we need to specify an X somewhere. And of course, the place with the maximum concentration will be where we first spilled that petroleum. So it's going to be at X equals 0. So when X equals 0 there, we have X of 0, which is a 1. And then the maximum concentration will simply be this value. So we then want to solve for when it reaches 10% of that original value. So we can take basically, we can specify a T1 and a T2, and we can set a ratio. So if we take C1 divided by C2 equals 0.1, then we can ratio out an estimated time there. So we can use this expression to look for that time. So that's basically how we can get the time taken to reach that 10% of that maximum value. Then on the other one, how long will it take to reach the dock? So we are given the distance from the dock. So we can simply enter this value for X here, and then solve for T. So again, we can put in for the concentration here, and then we've got the X value. Everything else is specified, and we can just solve for T. So it's just a matter of solving this expression. So you see, once you have the solution available, then you can answer interesting questions like that. So that's the value of being able to develop the material balance and being able to develop the boundary conditions. Because once you have those two things, you are able to propose a solution. And it's not the case we always have an analytical solution. We can get numerical solutions. Now, numerical solutions to high order ODEs, that's way beyond the scope of this course. But I'll show some results on that. We'll just talk about it at a high level and show some results. So in our research, we did quite a lot of that in our group. So there are some interesting problems to look at there. So even if you are not able to get a nice, neat analytical solution like this, you are always able to take a differential equation and solve it numerically. And so with your solution, you can see the types of questions you can ask and answer. So after investing all this time in a very abstract view of things, in just deriving equations all the time, we are now starting to see the interesting types of questions we can start to answer there. Okay, and that's basically it, these 3 problems for this tutorial. Any questions or comments there? All right, if not, we'll close it there. See you on Friday.